let's consider some application of our concept that the electric field is equal to minus the gradient of the potential. We calculated the potential for a ring along the axis that passes perpendicular to the plane of the ring. And let's say the ring has a charge Q. The radius of the ring is R. And we'll take our field point P here, which was a distance z away. And for this particular problem, we calculated that the potential at this field point was equal to 1 over 4 pi epsilon naught Q over z squared plus r squared to the 1/2. Now, we can use this result because we have the potential entirely along this direction. And if we wanted to find the electric field along the z-axis, and this is just along the z-axis, then in that case, the result, we can apply this result. It just becomes a simple, in general, the potential has a variety of terms in it because it's the gradient of the potential with an overall minus sign. But in this case, it reduces to a one-dimensional calculation, dvz dz, in the k-hat direction, because we're only looking at changes along this direction. And that's an easy function to differentiate. We have the minus sign on the outside. When we differentiate 1 over z squared plus r squared to the 1/2, we get a minus 1/2. We have the constant 1 over 4 pi epsilon naught. We have q over z squared plus r squared to the 3/2. And upstairs, we have a 2z. And so what we have for the z component of the electric field over the axis, we have the 2's cancel. We have our constant 1 over 4 pi epsilon naught qz over z squared plus r squared to the 3/2. And that is a simpler calculation than setting up Coulomb's law and taking vector decompositions and throwing away the alpha-axis components and then calculating the electric field along the z-axis. It's another way to calculate the electric field.